I'm Jim Heffron. These are my lessons in Calculus 2. So now we're at the payoff. I mean, we reached the point where we did the background work that we need to do, and we're ready to to be able to accomplish what we want to accomplish, which is to express functions as somehow an infinite sum. So let's get to it. This will be fun. Okay, so we had been carrying all along, ever since the motivation slides, we've been carrying these prototypes here, where we have on the left-hand side we have a familiar function, 1, 2, 3, 4, 5 of them, and on the right-hand side we're expressing that. We express that we intend to express it as a sum of an infinite number of terms here. So we want to see for each of these under what conditions we can write the left-hand side as equal to the right. And so I've been saying all along that we'll find, for example, that the left-hand side equals the right for some x's and not for others. So the first example that we saw for the geometric series is that the left-hand side equals the right, provided that the absolute value of x is less than 1. That is to say, provided that x is between -1 and +1, not including the endpoints. So provided that you're looking at an interval around 0. And presumably for the others here, we'll presumably find similar condition where for some x's the left-hand side equals the right-hand side. And we've done a lot of work along the way. We've defined a sum of an infinite series as the limit of the sequence of partial sums. Okay, and we've developed a number of tests, enough that maybe a person needs to have kind of it all written down in some organized way. Number of tests for convergence. We're mostly interested in convergence, and this gives us some idea why. We know that the right-hand side equals the left, provided that the right-hand side equals anything at all. All right, so far in the slides before this one, we focused on series like the one down here, where there are no variables on the right-hand side, and now that obviously differs from what we want to look at in the prototypes, where there are variables, where there's x's on the right-hand side. So what happens today is we look at series that have x's, and that's sort of the payoff. We're where we want to be here. Okay, so a power series in variable x with coefficient ci has this form. There's a coefficient c0 and a coefficient c1, and then there's a coefficient associated with x squared and a coefficient associated with x cubed, and etc. Down here we have again coefficient for the constant term, coefficient for the linear term, coefficient for the quadratic term. But we saw when we were doing Taylor polynomials that we sometimes want to center in that case the Taylor polynomials center at a number other than 0. So we would write then x minus a squared, x minus a cubed. So you can think of the line above here as being the a equals 0 case. Okay, I have a comment I want to make about what happens here when you're looking at the very initial term, the I equals 0 term, and also the x equals 0. So if I equals 0 and x equals 0, I'm not interested in ci. If I equals 0 and x equals 0, then I find myself looking at 0 to the 0. And a person can wonder about that, because suppose, for example, I don't want to use x, so I'm going to use y. Suppose, for example, you look at y to the 0, and you say y equals 5, y equals 4, y equals 3, y equals... So y equals 5 gives you 5 to the 0, which is 1. 4 to the 0 is 1. 3 to the 0 is 1. 2 to the 0 is 1, etc. So it sure looks like the answer for 0 to the 0, from that perspective, looks like the answer for 0 to the 0 should be 1. Okay, but of course there's a trick, otherwise I wouldn't be making a deal with this. What happens if you look at 0 to the y? If y is 5, 4, 3, 2, 1, etc. So 0 to the 5, 0. 0 to the 4, 0. 0 to the 3. Sure looking like the answer for 0 to the 0 should be 0. So it's not perfectly clear what 0 to the 0 should be. It turns out to be the case that of the two choices, that the one that is convenient, the one that proves to be the one you want, is you want to define 0 to the 0 to be 1. And in particular, we define 0 to the 0 to be 1 because then I'm looking at c0 times 1. And that's what I want. Okay, so in general, 0 to the 0 will define to be 1, even though there's some question about what's the right thing to do there. It turns out there is a right thing to do, and the right thing is that 0 to the 0 is 1. Okay, so we have power series. They kind of look like very, very long Taylor polynomials. Taylor polynomials where, if you look down the railroad tracks and they seem to go together way off in the distance. Well, this is a Taylor polynomial kind of thing where they're very long polynomials and they kind of blend together in the distance off toward infinity. That's what we're looking at. So there will be power series that converge for all x's, power series that converge for some x's and diverge for others. And we'll use tests like the kind of ones we developed, most in particular the ratio test, to determine where they converge. However, important to note that power series always converges at its center point. So let's look, for example, here at the center point of 0. For the top line, if you plug in x equals 0, you've got c0 plus c1 times 0 plus c2 times 0 squared plus c3 times 0. Oops, I wrote c2. I was supposed to write 0. Plus c3 times 0 cubed, etc. Now that obviously converges to c0. So every power series converges at its center. Okay, so what's the story? What's the story with convergence? Let's go through some problems and see where they converge and where they don't converge. And so I have some examples that are just supposed to illustrate the different things that can happen. Okay, so here's the first one, and I just pulled this out of nowhere. So let's see, there is no c0. We're starting with n equals 1. So here's a c1, and c2 is a half, and c3 is a third. We're looking at x minus 2 squared and x minus 2 cubed, etc. So this is centered at a equals 2. So just try to pick a fairly generic power series where there's nothing especially, in this special case. There doesn't seem to be any particular special case here. Okay, so to figure out where it converges, I'm going to apply a test, and specifically, I'm going to apply the ratio test. I'll note that x minus 2 could be negative. What if x is 1.9 or 0 or minus 100? So I'm going to need the absolute value bars. So I'll keep them around. So let's see here. Here is the n plus first term and the nth term. Right? When you take n plus 1, you get the numerator. When you take n, you get the denominator. Okay, and I'll do the algebra on that. Let's see. I have x minus 2, I inverted and multiplied. X minus 2 to the n plus 1 over x minus 2 to the n. And you see how n was on the bottom of the bottom there, so it ends up on top, etc. N plus 1 ends up on the bottom. So with some algebra here, there's n plus 1 many x minus 2's, and there's n many x minus 2's. So you cancel all but one of them, and you're left with x minus 2 in the numerator. The n and the n plus 1 stick around. Now here's the sort of one of the themes for the couple of examples that we're going to show. X minus 2 doesn't have anything to do with n. I mean, obviously n has something to do with n, and n minus 1 has something to do with n, but x minus 2 doesn't have anything to do with n. So I can break the fraction here that's in the absolute value bars. I can break this fraction into an x minus 2 and an n over n plus 1, and then bring the x minus 2 out. It's in absolute value bars because it could be negative. I brought the x minus 2 out, so I can't drop the absolute value bars because the x minus 2 could be negative for some x's. But I can bring the x minus 2 out because it doesn't have anything to do with n. That's to say, x minus 2 doesn't change when n goes to infinity. Okay, but that leaves me with the limit as n goes to infinity of n over n plus 1. I mean, come on, that's no trouble at all. If n is large, if n is 100 billion, then you've got 100 billion over 100 billion plus 1. That's essentially the number 1. So I've done the algebra, and I've got that applying the ratio test, that the limit is the absolute value of x minus 2. And remember, there's variables here, so x could be lots of x could be 50, x could be 7.4, x could be minus 6.5. So absolute value of x minus 2 times 1, and because it's a ratio test, I'm asking for which numbers is that limit, for which x's is absolute value of x minus 2 times 1 less than 1. That's what ratio test says. It says look to be less than 1. Okay, so when is absolute value of x minus 2 less than 1? And so there we go. The series is convergent where absolute value of x minus 2 is less than 1. If the absolute value of x minus 2 is greater than 1, then the series diverges. And if the absolute value of x minus 2 equals 1, then we can't make a conclusion. I'll get through those in a second. One way to think of this expression, absolute value of x minus 2 less than 1, is to read it this way. X is within 1 of 2. Okay? X is within 1 of 2. Okay, so I'm looking at a collection of numbers that are close to 2, namely strictly within 1 of 2. So this series is convergent, in fact absolutely convergent, when the number that you're looking at, x, is close to 2, and it diverges when x is far from 2. Okay, so what about the case when the ratio equals 1? So when the ratio equals 1, I'm looking at x is exactly 1 away from 2. I did closer than 1, I did further than 1, and we're thinking about the case where x is exactly 1 away from 2. All right, so 1 away from 2 means either being 3 or being 1. So I'm simply going to try those numbers in the original series up here. I'm going to try 3 and I'm going to try 1 and I'm going to see what I get. And then whatever we get is what we get. All right, so here we go. Let's try x equals 3, for example. Okay, so 3 minus 2 is 1. So this is 1 times 1. And this is 1/2 times 1 squared. And this is 1/3 times 1 cubed, etc. And so clearly what I'm looking at here is the harmonic series, and it diverges. We know because we did a lot of work, which is paying off right now. We did a lot of work about when you get divergence and convergence of numerical series, not power series, numerical series. And, we recognize the harmonic series, and it diverges. All right, let's try x equals 1. Let's see. If we try x equals 1, I'm looking at 1 times minus 1. Plus 1/2 times, let's see, what's minus 1 squared? So that's plus 1. And then plus 1/3 times minus 1 cubed, which is minus 1, etc. And I recognize that as the alternating harmonic series. And the alternating harmonic series we've seen converges. So again, the work that we did earlier, it's almost like we set it up so that we'd be ready for just exactly this moment. So with the work that we did earlier pays off. When x is 3, you're looking at the harmonic series and it diverges. When x is 1, you're looking at the alternating harmonic series and it converges. And in sum, we have this picture. Numbers that converge, x's for which the original series converges, are close to 2. Specifically, they are within 1 of 2. Strictly within 1 of 2. So if x is close to 2, how close? 1. If x is within 1 of 2, strictly, then you have convergence, in fact, absolute convergence. We'll talk about absolute by the end of this slide deck. So if you're within 1 of the number 2, then you absolutely converge if you're strictly within 1. If you are further than 1 from the number 2, if you're at, let's say 5 or 100 or 1,000 or minus 15. If you're more than 1 away from 2, if x is more than 1 away from 2, then the series diverges, the original series diverges. And exactly at 1, you get converges on the left and diverges on the right. Okay, and so this is a kind of a generic picture. This is kind of what can happen. You're always going to have sort of a plus and minus. In this case, we had 2 plus and minus 1. Then you'll have a left hand and a right hand that you're just simply going to check by hand. You're going to plug the left hand in, plug the right hand in, and cross my fingers that I'll be able to figure out the answer. Outside of that region, outside of the plus and minus region, we're looking at divergence. Okay, so need more than one example, of course, but the other examples have something of the same feel. Let's try them. Here's a second example, and again, this one happens to start with 0. So I'm looking at C0. C1 is a 1, C2 is a 2, C3 is a 6, C4 is a 24, C5 is 120, and I hope a person by this point recognizes that as k factorial. And I'm asking, where does it converge, where does it diverge? So I'm going to apply a test, namely I'm going to apply the ratio test. So the ratio test gives convergence when the limit is strictly less than 1. Here is the k plus 1th term. I got that by plugging in k plus 1. Here you notice that I did not get k factorial plus 1. I got k plus 1 factorial, and I got x to the k plus 1 power. And then on the bottom goes the kth term in the series. Okay, great. A certain amount of algebra happens. Let's see what happens here. So I guess there's x to the k plus 1 and x to the k, so I can cancel all but one of the x's, and there's that one x. And there's a k plus 1 factorial in the numerator and a k factorial in the denominator. And now the same thing happens that happened last time. Namely, I observe, as I observed last time, that x doesn't have anything to do with k. That is to say, when k goes to infinity, x does not change. X doesn't go anywhere, x just is x. So I break the fraction inside the absolute value bars into two halves, the part with x and the part with k's. Now the part with k's, those numbers are all positive, so I took the liberty of dropping the absolute value bars. But the part with x, I'm going to bring out past the limit sign. I'm a little worried about the k plus 1 factorial over k. We've been doing factorials a fair amount, but nonetheless, sometimes I find people are still confused or have forgot or something. So let me look at 5 factorial over 4 factorial. And that usually clears up the problem. So we get 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. And of course, all this stuff cancels, and we're just left with a 5, that is to say, with a k plus 1. Okay, so we've boiled the ratio test expression down to absolute value of x and limit as k goes to infinity of k plus 1. That clearly is infinity. So I'm now asking for which x's is it the case that absolute value of x times infinity is less than 1? For which x's is it the case that the absolute value of x times infinity is less than 1? And the answer is x equals 5 doesn't work. X equals minus 3 doesn't work, the absolute value of minus 3. And then times infinity does not give you something less than 1. So a person might say, well, the only thing, what about 0 if x is 0? So you have some question about the 0 times infinity case, with good reason. But if we go back to the source and we actually plug in what happens when x is 0, then you've got 1 plus 0 plus 0 plus 0. So clearly converges. So this power series converges only at its center. And I drew a picture, there we are, where it converged only at the center of x equals 0. Or you could say a equals 0, I guess. Okay, so again, trying to illustrate how you do the problems, but also illustrates the things that can happen. And so one thing that could happen is you could find that this limit over here, you could find, where's my pen? There it is. You could find that this limit over here is infinity. And so as a result, you get just a single point. You get sort of, in this case, a plus and minus 0, you could say, I suppose. Okay, next. So here we are trying another one, and just simply trying a couple to illustrate the point of exactly what happens here. Okay, so for which x's does this power series converge, and for which does it diverge? And clearly here I'm looking at a equals 1. It's centered at 1. I didn't bother to do this part down here. I'm trying to just help a person get up to speed. So I'm gradually sort of relaxing on some of the crutches. Okay, so let's try it. I mean, surprise, surprise, I'm going to apply the ratio test, and I'm going to ask, when do I get a limit that's strictly less than 1? Okay, here we go. So I took the k plus first term, and the kth term. And there's always some kind of algebra. You invert or multiply maybe, and then there's always some kind of canceling with the k plus 1 power and the k power. And I dropped a couple steps here. I skipped a couple steps. But we find ourselves looking at the x minus 1 absolute value and the k factorial over k plus 1 factorial. And we've seen in previous problems, we want to bring the x minus 1 out, and we want to evaluate the limit. What's the limit when k goes to infinity of 1 over k plus 1? And, if k gets to be 100 billion, 1 over 100 billion and 1 is an awfully small number. That is to say, the limit is 0. And now we find ourselves asking, when is the limit less than 1? Because that's what the ratio test tells me to ask. So when is it the case, for which x's is it the case, that the absolute value of x minus 1 times 0 is less than 1? And the answer is every x. If x is 1,000,000, absolute value of 1,000,000 minus 1, doesn't matter because you're multiplying it by 0. You're going to get something less than 1. So the power series converges absolutely, and again, we'll talk some more about absolutely by the end of this slide deck, converges absolutely for all real numbers. I didn't bother to draw the number line here. It didn't really fit on the page very well. But if I had drawn the number line, it would have been everything. I would have colored in everything. So in fact, what we're finding that is if the limit is 0, then in some ways you're getting sort of 0. You're getting a plus and minus infinity. It's a little bit silly to write, just like it was a little silly to write here a plus and minus 0. But okay, So what can happen is, in each case, you find yourself applying the ratio test. The powers of x cancel, x minus a, cancel, and you bring that expression x minus a absolute value out past the limit sign. And what's left is you're looking at the limit of the coefficients here, and you're asking, what is that limit? In some cases, when the limit was infinity, for example, I got plus and minus 0. When the limit was 0, I got plus and minus infinity. So there's a pattern to what's happening here. All right, so we've seen a lot now. We've seen exactly what happens. Everyone starts with the ratio test. Everyone goes through a set of algebraic expressions, and everyone ends up by asking, for which cases are you strictly less than 1? Okay, so we're ready for a practice. Then it seems to me the right thing to do here, what I urge a person to do, is to pause the video, give the problem a try, and then when you take out a piece of paper, write it down. When you come back here, I'll have the answer so you can check how you did. Okay, give you a second to pause the video. Okay, here we are back. I applied the ratio test. This is the n plus first term. This is the nth term. And you find yourself canceling the powers of x, cancel the powers of x, and there's just a single x. You cancel the powers of 2, and there's just a single 2. I brought the absolute value out, and I find myself looking at the limit of, I don't need the absolute value of 1/2. I can just write 1/2. So I'm asking for which x's is the absolute value of x times 1/2 strictly less than 1. So for which x's is the absolute value of x times 1/2 strictly less than 1? And the answer is for those x's where the absolute value of x is less than 2. So I'm asking for those x's that are within 2 of 0. The center of this series is 0. I'm asking, so the answer to my question is those x's which are strictly within 2 of the center of the series. If you're strictly greater than 2 away from the center of the series, for example, if x is 3 or if x is minus 3, then plugging in x would cause the series to diverge. And of course, we see the picture down at the bottom, within 2, strictly within 2 of the center, a equals 0. What about the boundary points? So you just simply have to plug them in. There's no formula here. You're just plugging them in. So if you try x equals 2, what do you get? And if you try x equals minus 2, what do you get? Okay, so we try x equals 2. Then I've got 1 plus 1/2 times 2, plus 1/4 times 2 squared, plus 1/8 times 2 cubed. All right, now I'll try plugging in minus 2. So you get 1 plus 1/2 times minus 2, plus 1/4 times, when you square, of course, so you get a positive. When you cube a negative number, of course, you get a negative. And so we get what we wrote down here. Clearly, this one diverges because the partial sums ping-pong back and forth between 1 and 0. And this one diverges because it adds to infinity. Okay, so the series diverges at both boundary points, both the left and right-hand boundary points. And so I've got this picture here, full picture of convergence or divergence. If you pick an x in here, then you're looking at converges. In fact, converges absolutely, and again, we're going to talk more about what absolutely means soon enough by the end of this slide deck. If x is out here, then you've got diverges. If x is exactly at the boundary, we check those sort of by hand, and we got, in both cases, diverge. Okay, great. So we see that there's a pattern. You always apply the ratio test. It's always the case that the powers of x's cancel, and you're left looking at something like the absolute value of the x expression. It's actually absolute value of x minus a. Absolute value of x minus a, and then you ask yourself, what is the limit? And figuring out what is the limit enables you to figure out what is its center. In this case, 0 plus and minus 2, but in general, it's center plus and minus some number. All right, so let's summarize. Each of those examples work the same way. You always apply the ratio test. Always the x minus a absolute value factors out, and we always get a region where the series converges. So we have a summary. I wrote it as a theorem, but it's really a summary. Every power series has a radius of convergence. Rho, that's the Greek letter rho. It's spelled R-H-O, and it's pronounced like row, row, row your boat. Okay, so every power series has a radius of convergence rho, and that radius of convergence could be 2, or it could be 0, or it could be infinity. So it's between 0 and infinity, including both endpoints. Could be 0, could be infinity. At the center point, the series converges. Inside the radius of convergence, for those x's where x is within, strictly within, rho of a, for those x's where x is within rho of a, the power series converges. It converges absolutely, but we don't need that just exactly right at this minute. We will soon. The second paragraph is the one that a person wants to refer to when you're doing the homework. You know, it's kind of the most handy one. We always find ourselves looking at the limit of the ratio of the coefficients, not the x part. The x part factors out. We always find ourselves looking at the limit of the ratio of the coefficients, the n plus first coefficient over the nth coefficient. And sometimes it's a finite number, like 0, for example, but sometimes it can be infinite. If capital R is 0, we saw a case like that, then the plus and minus is infinity. And I'll click back to that example. Here we go. When that limit was 0, we found ourselves with kind of a plus and minus infinity expression. But I don't want to click away and then come back. When that limit was infinity, we found ourselves looking at a plus and minus 0. And finally, the last case, and again, I'm going to go back to the summary in just 10 seconds. When that limit was 1/2, we found ourselves looking at plus and minus 2. Okay, so the summary says, oh, sorry, clicked once too many times. When capital R, when this limit, oops, darn it all. When this limit here, when capital R is 0, then you're looking at plus and minus infinity. When capital R is infinity, then you're looking at plus and minus 0. And otherwise, rho is 1 over R. And then the closing paragraph has, of course, more to say, but it's the middle paragraph that a person finds himself referring to more when you're doing the homework. If rho is finite, then for those x's that are more than rho away from a, I mean, it wouldn't make sense if rho was infinity for this sentence, so I left out infinity. For those x's that are strictly more than rho away from the center, a, the power series diverges. As to the boundary points, those x's which are exactly rho away from a. As to the boundary points, there are series that converge at both boundary points, series that converge at neither boundary point. There are series that converge on the right but not the left, and there are series that converge on the left and not the right. So all 4 things can happen. Okay, so in summary here, we always get a plus and minus, always get a plus and minus. The formula for the plus and minus is in the second paragraph. Okay, so we get not that anything in the summary is dopey, but just the second paragraph is what you find yourself saying over and over again. Okay, let's go through then. We're going through the summary, which reduces sort of some of the things that happen in every single problem. So here we go. I'm looking at a series. It's 1 over the square root of n, and it's clearly centered at a equals minus 2. So a equals minus 2. Because this is x minus a minus 2. That's how you end up with x plus 2. And the C, this is Cn. Cn is 1 over radical n. Obviously, I didn't want to have 1 over radical 0, so I started the series at 1. Okay? I'm applying the theorem from the prior slide. So the series is centered at a equals minus 2. To find the plus and minus, the interval around that center, find capital R. So you look at C sub n plus 1 over C sub n. That's the 1 over radical n plus 1 and 1 over radical n. And let's see, so then when you invert and multiply, you get a radical n over radical n plus 1. And so you find yourself taking the limit as n goes to infinity of square root of n over n plus 1. And when n goes to infinity, if n is 100 million over 100 million plus 1 is basically 1. When you take the square root, you're basically 1. We're looking at a limit of 1. So the radius of convergence is 1 over r. So that's 1 over 1, so that's 1. Rho equals 1. So the series converges. It converges absolutely, but anyway, converges for all x's where it is the case that x is strictly within 1 of negative 2. Again, read this expression as x is strictly within 1 of negative 2. And here, I said it a different way. It's the interval that runs from minus 3 to minus 1, not including either endpoint. And the series diverges when x is further than 1, strictly further than 1, away from negative 2. You can see the picture down at the bottom of the slide. All right, well, what about the boundaries? The last thing to cover, what if you're exactly 1 away from negative 2? So if you're exactly 1 away from negative 2, plugging negative 3 into the original series. Plugging negative 3 into the original series gives you this. Plugging minus 1 into the original series now, I sometimes have folks confused about what I'm plugging into. If you plug minus 1 into the original series, x equals minus 1. X equals minus 1 into the original series, then you get this. And you can see here that we're looking at an alternating p-series, so it converges because the alternating p-series test. And here you can see that this is a regular p-series and that it diverges because of the regular p-series test. Okay, so we have the summary picture down here. Converges at one boundary point, diverges at the other. So any of the four things can happen. You can have darken in both circles. You can have darken in neither circle. You could have darken in the left but not the right. And you could have darken in the right but not the left. All four things can happen. There are series for which any of the four could, cover. Okay? So practice. Time to stop the video, give it a try, and come back and see what the answer is. I'll give you a second to pause the video. Okay, we're back. So the series, this doesn't say like x minus 5 or x minus negative 3. Instead, it just says x. So the series is centered at 0. When you apply the theorem, you looking for capital R, you take the I plus first coefficient and the ith coefficient. And here, the coefficient Ci is a 1 over I plus 1. Okay, not paying attention to the x's because we saw when we did the first couple of examples that the x's always factor out. So paying attention only to the coefficients. All right, so let's see. If you, forgive me, I forgot the minus 1 to the I. Minus 1 to the I. Okay, so if you write down what happens when you plug an I plus 1 into this expression, you get minus 1 to the I plus 1. And then on the bottom of the fraction, you get I plus 2, right? Because it was I plus 1, now it's I plus 1 plus 1. And on the bottom goes minus 1 to the I over I plus 1. You invert and multiply. Because it sets absolute value bars, the minus 1s don't make any difference, so you can just skip those. And you end up, when all the smoke clears, with an I plus 1 over an I plus 2. Take the limit as I goes to infinity. If I is 100 billion, come on, you're just looking at a limit of 1. So capital R is 1, so the radius of convergence is 1 over 1, which is 1. This series converges for x's strictly between minus 1 and positive 1. It diverges when x is further than that, when x is strictly less than minus 1 or when x is strictly greater than positive 1. As to the boundary, at x equals 1, we have so-and-so, and at x equals minus 1, we have this and that. When we go through the details here, when you plug in x equals 1 into this series, Okay, again, I sometimes have folks confused about where you plug in the x equals 1. I'm plugging x equals 1 into this series. And you can see I'm getting minus 1 to the I, so it's going to alternate sign. 1, when you plug x equals 1, the numerator is just 1, and you're over I plus 1. So this is a version of the alternating harmonic series. So alternating harmonic series converges. At x equals minus 1, you have in this expression, when you plug minus 1 in here, you can see that the numerator is going to be minus 1 to the I. Minus 1 to the I times minus 1 to the I is going to just give you 1, because anything squared is going to be positive. Anyway, you just get 1. And so you're looking at a 1 over I plus 1. That's a version of the harmonic series, so it diverges. And therefore, we get converges on one side and diverges on the other. And so there's the interval of convergence. Okay, next one. Again, simply applying the theorem from the prior slide. That's 2 slides ago. Okay, give you a second to pause the video. Okay, great. So this series clearly is centered at a equals 2. And I'm looking at capital R here by taking c sub I plus 1 over c sub I. So let's see here. C sub I is, we're looking at 1 over I plus 1 times 3 to the I. So c sub I plus 1, we've got an I plus 1 in the bottom and a 3 to the I plus 1 in the bottom. And c sub I is we got an I and a 3 to the I. I mean, you invert, you multiply, you do all that kind of business. You end up with a capital R of 1/3. So the radius of convergence is going to be 1 over 1/3, which is 3. Oh, I spelled center wrong. Sorry about that. The center is a equals 2, so the series converges, absolutely, for a plus and minus 3, that is to say 2 plus and minus 3. So I'm going down to minus 1 and up to 5, strictly between minus 1 and 5. It diverges outside that zone, and exactly at minus 1 or exactly at 5, you just simply have to plug them in. Plug in minus 1 and plug in 5. When you plug in minus 1, something happens. When you plug in 5, something happens. And it's just, there is no formula for that. You're just simply doing the kinds of things that we have been doing now for a number of videos. We've been getting series of all numbers, no x's, series of all numbers, and we recognize what we have. So when x equals minus 1, the alternating series test gives convergence, while when x equals 5, you're looking at a harmonic series, so it diverges. When x equals 5, you're looking at a harmonic series, so it diverges. Is that right? Oh yes, that's right, because if you plug in x equals 5, you've got 5 minus 2 to the I, that's 3 to the I, and so we're in business. So it's some version of the harmonic series. Okay, so really we're just relying here on the fact that we've worked for some time now to figure out a large number of cases that gives us answers. Okay, so all the work we've been doing pays off exactly at this moment. Okay, great. Okay, so we've gone through and done power series. We've shown how you can put x's into these infinite series, and we're well on our way to understanding how the left-hand side of the prototype table can be equal to the right-hand side of the prototype table, but only for some x's. Okay, so we want to talk now about the equality between things on the left and things on the right. That is to say, how can a function be equal to the power series? So I'll say that this is a relatively long set of slides. So this might be a good place. You might want to pause the video, go get a drink of water. But anyway, so I'm going to go on. So power series converge for some x's. Where they converge, I mean, if they go to infinity, they don't define a function. But where they do converge, they define a real number function that takes in one input, x, and returns one output, f of x. So I have f of x and I have f sub a of x, just to highlight the role of a, of the center a. We say that the series represents the function. Okay, I put equality. There's nothing wrong with the word equality, but I'm trying to express that somehow we've expanded the series to make an infinite series come out equal to the thing on the left, the function. Okay, so let's take a typical example here, the geometric series with common ratio x. And we've done a good amount of geometric series with common ratio x, so I don't feel like we need to give 5 examples of it. We know that it converges for x's strictly between -1 and +1, and it diverges elsewhere. Where it converges, we know that it gives the function 1 over 1 minus x. I mean, we did this. We did the formula for the geometric series with common ratio 1, so 1 over 1 minus x. Okay, so here is I drew a graph of 1 over 1 minus x. And I specifically identified what happens to 1 over 1 minus x in the region of interest. I have diverges at the boundary points. Of course, 1 over 1 minus x, of course, when you take x equals 1, you get some kind of vertical asymptote. So there it is, there's the vertical asymptote. And at the other end, we just find that it is just simply not defined. The function capital F is just simply not defined at -1. It just isn't. 1 over 1 minus x is defined at -1, but the sum of these is just simply not defined at -1. Okay, so in the region on which the infinite series is defined, it's equal to a perfectly ordinary and familiar algebraic expression. In the region where the infinite series is not defined, it doesn't equal anything. Okay, so that picture shows that. Next up, one of our prototypes is ln of x plus 1. And we, in the prototype table, we have it equal to this expression here. Do you see that the denominators are x over 1, 2, 3, 4, and it changes sign. So we're used to both of those cases. We're used to there being denominators, and we're used to changing sign until we get this expression here. We can apply the radius of convergence like we've been doing the radius of convergence so far. There's a c sub I plus 1. There's c sub I. When you invert and multiply, you end up with I over I plus 1, and clearly that limit is 1. So and I'm sorry, I forgot to remark that the center here is a equals 0. So we're looking at a 0 plus and minus 1. At x equals -1, we get the negative of the harmonic series, so it diverges. At x equals 1, we get the alternating harmonic series, so it converges. Okay, so I am looking at here's the interval on which the infinite series right here makes sense. For x's outside of that region, that interval simply doesn't make sense. It just simply it diverges. So, but inside of that interval, the expression up there makes perfectly good sense. In the region for which we are looking at that series, the interval on which it's defined, we get that it is equal to ln of x plus 1. Okay, and again, we know what happens at one end of that interval. We know that at -1, ln of x plus 1 looks like ln of x plus 0. There's a vertical asymptote there. And at the other end, although that boundary point is defined, nonetheless it stops there. The infinite series just simply stops making sense there. So we get a function, perfectly good function, in the interval on which the series converges. That function is ln of x plus 1. Outside of the interval on which the series converges, it isn't anything. It doesn't converge. Okay, so a capital F is just simply not defined outside that interval. Okay, so I want to talk. I've been promising to talk now for a period of time about the word absolutely in converges absolutely, and now's the time. So we have what amounts to very long polynomials. I made the analogy between when you look at railroad tracks sort of converging off into the distance. Well, here that's what we're looking at. We're looking at very, very long, very, very long polynomials. Under what circumstances can you treat these as polynomials? Can you do things like divide all the coefficients by 5? Or say substitute x squared for x? Under what circumstance can you do that? So on the next slide, it's going to give the rules, going to give the formulas, but as an overview, as long as the input is such that the power series converges absolutely, there's the word absolutely, then the series has many of the algebraic properties of a polynomial. So the series is well behaved as long as x is such that the power series converges absolutely. Consequently, inside the radius of convergence, by the ratio test, the power series inside its radius of convergence rho converges absolutely. So inside its radius of convergence, a power series is like an ordinary polynomial, except it's of unbounded degree. So you can do things like integrate term by term, differentiate term by term. All the things you can do with a polynomial, all the things that make polynomials so easy in a calculus class, all work as long as you are at an x where the power series converges absolutely. So things are nice, you know, it's happy land if you're at an x where the power series converges absolutely. Okay, so maybe I should make this in red. Absolutely. Okay, next slide. Here we go. They're the rules, and there's a lot of rules. I'm going to read through them, but there's too many rules really for a person to have make much sense of it. But I'm a person who I like to put everything in one place. I'm a joiner rather than a splitter, and that way when when I'm trying to do the homework, I refer back to that one place. I like that. Okay, so do you see the word absolutely here? You see it there? Absolutely. So assume that you have series 1 or 2 or 3 or 4, but I only need 2 to state the rules. Assume that you have series that converge absolutely on some open interval. Then those functions are continuous. I mean, continuity is a great thing, very handy property to have. Also, you can add the 2 series term by term. You can multiply the 2 series by a constant. You can multiply a series by a constant. You can subtract the 2 series term by term. So you can do the sort of ordinary polynomial manipulation that you want to do so many times. You can add f plus g. You can multiply the entire expression by x squared or x cubed or x to the 9th if for some reason that's convenient. Okay. You can substitute in where it says x, you can substitute 5 times x squared. Or you could substitute 1/7 times x cubed in for x. And you'll get what you think you should get. And finally, sort of the big payoff, you can take the term by term derivative and antiderivative. So I happen to work with f just because it's alphabetically first. So the derivative of f, if I was to ask you what is the derivative of the expression on the right-hand side here, you'd say, well, the derivative of the constant c0, that's 0. Derivative of c1x is c1, you'd say. Yeah. Derivative of c2x squared is a 2c2 times x. Yeah, etc. And antiderivative. What's the antiderivative of lowercase f? Well, the antiderivative of c0 is going to be c0x. The antiderivative of c1x is going to be 1/2 c1x squared. The antiderivative of c2x is going to be 1/3 c2x cubed, etc. Don't forget the plus capital C, and that's what it says. Okay, and they give you the derivative and antiderivative function. Okay, so the short version is we're so keen on the word absolutely because it enables us to do manipulations that treat infinite cases, infinite objects, as though they were finite objects, that treat infinite series as though they were finite polynomials. Okay, and of course I have to illustrate why that's useful in any way, but I'm going to do that in the next couple slides. I like to gather all the rules together on one slide, that's all. Okay, so let's try a couple. It so happens in the ones that we try, we're going to always be starting with the geometric series. It's not that that's the only series for which it works. It's just that, when you're trying to, as a math teacher, when you're trying to make a point, you don't want to change everything at once. You just want to illustrate how you manipulate sort of one thing and then do another and then another. We're only ever going to do the one. Okay, so I'm going to start with the geometric series and show how to manipulate it, to do a number of things with it, to try to illustrate the use of these rules. I'm always using the geometric series, not because no other series works, but rather because I'm trying to show the manipulation rather than change the series. Okay, so in each of these examples, I'm going to use the above theorem to manipulate the geometric series. Spelled series wrong, sorry about that. Geometric series. I could use other series, but I'm sticking to geometric just because that's how math teaching works. All right, so I want to find the series for 1 over 6 minus x. I know the series for 1 over 1 minus x. Remember, it's 1 plus x squared plus x cubed. How do you get the series for 1 over 6 minus x? I mean, I'm starting small because, again, that's how math teaching works. So I told you what to do. I said first use rule 4 and then use rule 2. So I'm going to flip back just 10 seconds to remind you what rule 4 is and what rule 2 is. So rule 4 says you can substitute a times x to the m in for x. Rule 2. Rule 2 says that you can do things like multiply every term by, in this case it's going to be 6, but multiply every term by a constant. If you took every term and multiply by 6, you would get 6 times, oh, I lost my pen again, darn it. You would get 6 times f of x, 6 times f of x, 6c0, 6c1, 6c2, etc. Okay, so that's rule 4 and rule 2. Here we go. Start with the geometric series. I'm using x's instead of r's. I don't know. I could have used r's. I used x. Using rule 4, I'm replacing x with x over 6. So I'm replacing x with 1/6 times x. Okay, what's the point of that? And the point of that is that when you do the algebra, you end up with the 6 minus x that I want. I want 6 minus x in the denominator, and I end up with 6 minus x in the denominator. Now there's a 6 times, it's 6 times bigger than I want, but you know what's going to happen. I'm going to divide by 6. Anyway, that's what happens when I replace x with x over 6 on the left. When I replace x with x over 6 on the right, here is x over x. Sorry, I'm losing my place. X here, x got replaced with x over 6. X squared is going to be replaced with, so over 6 quantity squared, x squared. X cubed, you replace the x with x over 6 and you end up with x cubed over 6 cubed, and etc. Okay, so that was rule 4. I got what I wanted, the 6 minus x on the bottom. I know I have something I don't want on the top, but I'll get rid of it in a second. Just give me a second. But here, I got what I wanted on the bottom. Next up, it says use rule 2 and divide both sides by 6. Okay, so I divide both sides by 6, and I do indeed get what I wanted. I wanted that, and I got that. I'm dividing both sides by 6. Okay, so we divide the 1 by 6, and you get a 1/6. Divide the 1 over 6 by 6, and you get a 1 over 6 quantity squared. Divide the 1 over 6 squared by 6, you get a 1 over 6 quantity cubed, and so there we go. Okay, so this I manipulated using the rules on the prior slide that are allowed because we have absolute convergence. I used the rules on the prior slide to manipulate the series from, I started with 1 over 1 minus x, and I ended with 1 over 6 minus x. Okay, so dot, 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 dot. I got from the one place to the other place. Okay, going to do a couple more. Starting from the geometric series, use the rules. So I'm not saying what the rules are. Use the rules to get the power series representing ln of 1 minus x. ln of 1 minus x. Okay, so I start with 1 over 1 minus x, and that's of course equal to 1 plus x squared plus x cubed etc. And so we spot that ln of 1 minus x is the antiderivative of minus 1 over 1 minus x. So clearly I'm going to want to put minus, 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 and I'll take the antiderivative. So the antiderivative of minus 1 over 1 minus x is the antiderivative of that series term by term, and I factored out the minus 1. So the antiderivative of this series, well, the antiderivative of 1 is x. The antiderivative of x is 1/2 x squared. The antiderivative of x squared is 1/3 x cubed, etc. Don't forget the capital C. And then the minus 1 is just along for the ride. And then I just simply summarized on this line. If you're interested in capital C, you can say to yourself, ln of 1 minus x equals, you can say to yourself, I'll plug in x equals 0 to both sides. When I plug in x equals 0 to both sides, this expression becomes 0, and so I just get capital C. When I plug in x equals 0 to this side, I'm looking at ln of 1, which I know is 0. So capital C equals 0. Okay, so I manipulated the geometric series to get another series using the rules, and the rules are only allowed because we're looking at absolute convergence inside the radius of convergence. Okay, not going to do tons more, but a couple more. One of our prototype series is ln of x plus 1 equals this expression here. I want to derive it from the geometric series, of course, using the rules. So here's the geometric series. I don't want 1 minus x. I want 1 plus x. So I replaced the x with a minus x. There is a rule that says you can go through. There is a rule that says you can substitute minus x to the 1 power, a equals minus 1, minus x to the 1 power into the series, and it'll converge absolutely. So that's what I'm doing. I'm substituting minus 1 x into the, I don't want to lose my way, minus 1 x into the left and right hand sides of this series. So when you substitute minus x for x here, you get 1 minus a minus x, and there I am. When you substitute minus x, unchanged, substitute minus x, of course when you square, the minus x just becomes x squared. Substitute minus x, substitute minus, etc. And now ln is the absolute, ln of x plus 1 plus capital C is the integral of 1 over 1 plus x dx. All right, so we recognize the antiderivative formula that ln of 1 over 1 plus x, ln of x plus 1 is going to be, plus capital C is going to be the antiderivative. So I'm taking the antiderivative. Antiderivative of 1 is x. Antiderivative of minus x is minus x squared over 2. Antiderivative of x squared is x cubed over 3. Antiderivative of minus x cubed is minus x to the 4. You see. So you get, in summary, this expression here. Into this formula, if you plug in x equals 0, you get ln of 1 plus capital C, and you plug in x equals 0, you get capital C there. So you're looking at 0 plus capital C. So you just get set the value of C at 0 by plugging in x equals 0. Okay. Okay. Practice. So going to be 2 practices, and that'll end us for the day. So starting from the geometric series, get the power series representing 1 over 1 minus x squared by using Rule 5. I thought it would be helpful to tell you the rule. So 1 over 1 minus x squared, and as usual, I'm going to urge that you pause the video and come back and have a look, and go back and look at Rule 5 and see if you can. Maybe I'll take you back to Rule 5. Go back and look at Rule 5. Rule 5 here talks about differentiating and anti-differentiating term by term. So there we are. Whoops, went too far. Okay, by using Rule 5 to take the derivative. Okay, give you a second to pause the video. Okay, great. So the derivative of 1 over 1 minus x, the derivative of 1 over 1 minus x, this is 1 over 1 minus x. The derivative of 1 over 1 minus x, here it is you know, we know how to take the derivative. It's a chain rule, says it's minus 1 times 1 minus x to the minus 2 power, and then don't forget to take the derivative of what's inside to be minus 1. I know the minus 1 cancels with the minus 1, and you end up with 1 minus x to the minus 2 power. That's what we're asked for. So similarly, I find myself taking the derivative of the allied series. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared, etc. And so there's the series. Okay. Last one. Use the geometric series to derive the series for arctan. And so I'll give you a second to pause the video. Okay, great. So we know the derivative of arctan is 1 over 1 plus x squared. So if I can get the series for 1 over 1 plus x squared, I'll be in business. So I'm starting with the derivative, starting with the geometric series. There it is, the geometric series, and I'm looking to get 1 over 1 plus x squared. So I think to substitute for x, to substitute the expression minus x squared. And we have a rule that says you can go through and replace all the x's by a times x to the m, as long as you don't end up with negative powers, which we don't. Okay, so I replace the x with a minus x squared. You replace the x with a minus x squared. So when you replace the x with a minus x squared, you get this. Replace the x with a minus x squared, replace the x with a minus x squared, replace the x, etc. There we go. When you take the antiderivative, you're looking at arctan. So the antiderivative, okay, antiderivative of 1 is x, antiderivative of minus x squared is minus x cubed over 3. Antiderivative of x to the 4th is x to the 5th over 5. Antiderivative, you get the idea, and we end up with this expression here. Okay, oops, I forgot the plus capital C. Oops, minus 1 point for me, plus capital C. Except that you can establish that capital C is 0 by plugging in x equals 0. Okay, so clearly what we have is that if you are in a context where you have absolute convergence of the infinite series, then you can do all kinds of manipulations and derive all kinds of expressions, all kinds of formula manipulations to give you things that you want to know. Okay, so all along here for the past couple of videos, we've been saying that this is absolutely convergent, and a person could say, why are we doing that? What's so interesting? And the answer is, what's interesting is that you can do all kinds of ways of handling infinite series as though they were polynomials and get all kinds of answers that we want. Okay, long video, but a video that shows the payoff, so I think very satisfying video. Okay, very good.